So I try to bring also many concepts in this so I can remind you of those definitions again, if you noticed. If you have A and B or n by n matrix and matrices, and I assume A is similar to B, then the theorem is that the characteristic polynomial of A is equal to the characteristic polynomial of B. I think this is a doable one for all of you in here at this point, at this stage. So this is kind of on the order of what your proof should be like at this stage. Some of the other ones I showed you are a little harder than what I think you should be capable of at this stage. So this is what I know. Say again?
A equals B. Is that supposed to be B for diagonal between B and B?
No, it's only going to be diagonal if it's diagonalizable.
Oh, okay.
Right? So this is just the definition is similar.
Oh, so is that similar between B and B?
This means that there exists a matrix P that's invertible so that A is equal to P inverse B.
So what letter is it?
B.
It's B.
Yes.
Okay.
You only have a diagonal matrix if it's diagonalizable. So there's nothing about diagonalizable in this theorem.
Got it.
Just says A is this is the definition of matrices being similar.
Yeah. No, I just got similar but letter.
Right. Yeah, I thought D too, and I made it B probably. So that's the definition of similar. And what we're supposed to show is the characteristic polynomials are equal. So remember Tyler had asked earlier, like, when do you have to play around with it? This is not one you play around with. This, you know what characteristic polynomial is. The determinant of A minus lambda I. And the characteristic polynomial of B is determinant of B minus lambda I. And you really don't even have to write down the copy and paste business. You can go straight to it, right? So at this stage, I think it should be doable to this point. So I know where I have to start, and I know where I have to end. So I call this a stringing proof because you just start from one end of the show and then introduce your no inside that show and hope you get to that end. So let's see how it works. A minus lambda I, that's where I start. Well, why would I do the next step? Well, that's all I know. I don't know anything else. So A is P inverse BP, and I know that my end goal has to have a B in it. So this is how to get the B into play. So that comes from the hypothesis dropping it in. If you haven't used the hypothesis in your proof, something was wrong. That's a big flag, something went wrong. So the next step, all I did is I rewrote I as P inverse P. Now why would I do that? Well, I want to get rid of those P's. And the only way to get rid of those P's is to make a P to factor out somehow. So I rewrote the I so that it had a P in it so I could do something with it. So I'm using here that I is P inverse times P. So I'm going to factor the P inverse out to the left and factor out the P out to the right. I knew that I was going to do this at that step. That's why I did that step. So I look at it, and why would I know to do that? I've seen it before. So now you've seen it before. So when you see something similar to this kind of problem, you would use that same trick again. You've seen some things before. So I just copied and pasted the last step on the previous. This is where I was after the factoring. The P inverse gets factored out. This is the property of determinants, that you have a determinant of a multiple of things, then you can separate them out. And I know that also the determinant of P inverse is 1 over the determinant of P. They swipe out, and I'm left with the other end.
So the whole idea of those few steps was to be able to separate it easily.
Yes. Yes. I have had people come and tell me as they were helping me with something like this at your level, they would say, oh, this is easy. It's easy if you've seen it before. And this is one of those kind of things, if you've seen it a few times, like, oh, I've done this calculation for you. I've looked back at the lecture notes. I've done it for something else. So it's easy if you've seen it a few times. So that's a property of determinants that I just used, that 1 over P business. I'm going to show you why that works next. So how would you do this proof? You kind of have to know something. And this is kind of proof where if you organized everything correctly, I would give you most of the credit, because I would think that if you sat around and played with it, you'd get it, you know, the last part. So here's a mini proof. This is probably exam 1 type proof. prove that the determinant of A is really 1 over the determinant of A inverse, if A is an invertible matrix. How do you prove something like that? Well, if something's invertible, then by definition, that's the definition of invertible. A times A inverse is equal to I, right? So I just did that and slapped on the determinant symbols on both sides. But the determinant of I is 1. I'm going to prove that for you too. I realized, I don't think I've ever proved that for you guys. So I'm going to prove that for you too. And that's all she wrote. We're done. Because if I have A times A inverse in determinants is equal to 1, then I can solve and I get both of these identities. That if I divide both sides by A inverse, I get this one. And if I divide both sides by the determinant of A, I get that one. So why is that true? I remember learning how many of you have seen induction proofs before? Just seen them. You haven't? I had to do it in high school in a class called Math Analysis. I went to rodeo town school, so if I had it, I'm sure you guys had it, have seen it somewhere. So when I saw people doing this, I imitated and I did it. And I don't think I really understood what I was doing, but it was that thing where you start out with show true for n equals 1, assume true for n equals k, use that to prove it true for n equals k plus 1.
Oh, yeah.
You've seen it?
Yeah.
That was discrete math.
You should have seen it in discrete math. You saw it? You've seen it, right?
Yeah.
No? Okay. All right, when you go to Dr. Cutler's class and he asks you, have you seen math induction before, you have to say yes. Because that's one of his irritations in upper level classes. The students say no, and then I say, that can't be right. They must have seen it before. Because I went to rodeo town school and we saw it. We had rodeo town math teachers too, so it's like, I hope they don't watch this YouTube video.
It was only discrete math. If they didn't have discrete math, they don't know it.
They should, because I had it in high school.
That's why.
I didn't go to a very good high school. Academically good. In case people from my high school are listening to this on YouTube for whatever reason, I don't know why they would be doing that, but not anything flaw in character, it's just that it was not an academically setting you up to do very brilliant things afterwards with math induction. So why is this true? Well, the obvious way, if you wanted to go prove something like this, is just to start with an I and start finding the determinant of I and see what happens. What I noticed right away is if I do the minors, just this little trick, I get 1 times an identical matrix that looks like the big matrix, but it's 1 knocked down smaller in size. And so if I kept doing that over and over, I would just get a bunch of 1s all the way down till I got to a 2 by 2. Right? It's a pattern. So I get, but the 2 by 2, I can just do it. It turns out to be 1. But that's not a proof. That just, because that's saying, okay, I'm going to get 1 smaller, I'm going to get 1 smaller, and this is that's a hand waving proof. How would you do this in general? Well, I can actually calculate this for n equals 2. It works. I can use that information to show it's true for n equals 3. Because I just take the answer I got for n equals 2 and plug it in here. Then I could do the same thing for n equals 4. I could say, okay, I know the answer for n equals 3. I can take this n equals 4 by 4 matrix and break it down, and I get 1 times a 3 by 3 matrix, but I just did that just now, so I can plug that answer in, and I get the answer for n equals 4. And I can see eyes are starting to droop. Getting slightly sleepy, like, you get the point. I can't keep doing this. I can't just keep going, okay, now let's do n equals 5. Now let's do n equals 6 and use n equals 5 to do that. Now let's use n equals 6 and do 7 to do that. So you say, okay, the process is the same as I go step by step. So I'm just going to assume it's true for the kth. Like I did it all the way to the kth one. Just pretend I did it all the way to the kth one. And I'm going to use that information to go to the k plus 4. That's the algorithm. I've done it in general. That's what we call a math induction proof. And it's used when you have to do, when it's a kind of a natural number progression. So I have to show 1 to get it to prove 2, and then I use 2 to prove 3, and use 3 to prove 4. And then I get tired and say, well, I can just do this symbolically. I'm just doing the process. So I'm going to assume it's true for the kth one, that I pretend I did it all the way up to the kth one, I got sick of it, I'm going to use that information to do the k plus first. So I just write down the symbols to explain myself. This is the k plus first by k plus first one. I know by breaking it out into minors, I'm going to get this one. But that one I know the answer from the previous assumption. Right? I know that answer from that assumption that I pretended I did it all the way up to the kth step. So we call that the induction hypothesis. And so we say by induction we have, it's true, since that process is true, it's true for all of them. So I remember actually learning this. The way they tell you to do it is they say, show it true for n equals 1. That's the first step. Assume it's true for n equals k. And then show it's true, use that to show it's true for n equals k plus 1. I had no idea why I was going through the steps. I was only doing it because the teacher said to do it that way. And it dawned on me somewhere along the line where I was working out some of these problems, like, oh, I don't really feel like I really did the n equals 1 case right, so I'm going to do n equals 2. Like, I see what's going on. I'm using n equals 1 to do n equals 2. I got it. That's what you're doing. You're like, trying to rotely go through it and do n equals 1 to n equals 2, n equals 2 to n equals 3, and then you get sick of it and say, I'm going to do it symbolically. There's another way to do this problem, but I thought it was a great way to get that induction proof into your diet. So you can tell Dr. Cutler that you had seen an induction proof before, and you know the standard answer if he says, have you seen an induction proof before?
No.
No.
No, we had Dr. Salk.
You had Dr. Salk. Because this class is supposed to be a feeder into those classes, so that's his idea. And we do a lot of them in number theory, induction proofs, because number theory is about a lot about natural numbers. So you have to prove one to get to the other. Here's the second way, it's real slick. I squared's I, because that's what I does. It doesn't do anything, right? You multiply it twice and you get I back. But then I can slap on determinants on both sides, and then I can pull them apart by property of determinants. And because I is invertible, its determinant's not 0, so I can cancel out of both sides. And I get determinant I is 1.
That's a lot easier.
There's actually a thing, I don't know if it's there around anymore. I think the MAA publishes it, where you can publish a sweeter looking proof. So I don't know if you know the history of Fermat's last theorem and the whole, like, there's these big open problems. You think that all of math has been solved, it hasn't. And there's these problems that are around that are really simple to state, that people are really interested in, and they haven't proved them before. I'll give you two of them that haven't been proved even yet. One is called Goldbach's conjecture. I don't know if you've heard of that one. So if you take any even number, you can write it as a sum of two primes. And just think about it. Take 8. It's 5 plus 3. Take 14. 7 plus 7. Okay, so you can do this. The problem with this statement is it's a conjecture. It's not been proved yet. You can take computers and go out far enough, but you still have far enough to go, right? You still have an infinite number of cases to go. So these problems intrigue people, and they really try to prove them. So there's one called Fermat's last theorem, where there's a lawyer named Fermat, and he actually came home in the evening and just played around with math. And I think a lot of lawyers do this for whatever reason. I'm not quite sure. But he had a series of problems he wrote in the margins, like, I have a beautiful proof for this, but I don't have space here to write the proof, so I'm just going to leave the question in the margin. So his theorem that he wrote, he had a proof for, was never solved, and people tried to solve it for 300 years. And there's a professor from Princeton named Andrew Wiles who spent 7 years up in his attic and ended up proving Fermat's last theorem. So as soon as he proved it, it was like a huge proof that he sent and submitted, and then they had to review it, and so it was like a big deal, and it was not accessible. So someone else read it and wrote a cleaner proof, and I actually have a graduate text that I could teach out of technically. Maybe I wouldn't have many students sitting in class anymore, but I could teach out of it technically at the graduate level here. So somebody's rewritten the proof and made it cleaner and nicer and easier to read. And so there's a market for that.
So the person who got full credit, like the person that cleaned it up, didn't get any credit for it? Because he just kind of was...
I mean, he got his name on a book. Right?
Yeah.
Got something. Andrew Wiles, when he wrote this, there's actually a documentary. It's a really well done documentary in PBS where it goes through Andrew Wiles trying to solve this problem and his problems, issues with it. When he revealed that he has the proof, it's one of the most unusual cases of mathematics. Mathematicians talk to each other about mathematics, we're very open about what we're doing, and people share and give credit. I think it's because there's no money involved. So, and he didn't share what he was doing with anybody for a period of 7 years. And so nobody knew what he was working on. But he drew upon many ideas in mathematics to come up with his proof, and then he revealed that he has a proof of Fermat's last theorem, and he announced it in a conference, and he presented the proof. He was on the cover of People magazine, and it was like a big deal. And as his paper was being reviewed, somebody found a flaw in the proof. But now that he said he's working on it, he's got this far on it, and he's presented the ideas, it's open for anybody to go and solve it. And so there was a few months there where he was really stressed out, because if he wasn't the person that could fill that gap and clean up that proof and fix that error, then someone else could solve it. And there's plenty of smart people out there that are willing to try. Like, everybody's intrigued by problems like this. Math is an interesting field.